Okay, number 18 seems a little overwhelming when you look at it, but you should be able to get through parts of this at least. First of all, they tell you that you have some solvent J that contains carbon, hydrogen, and chlorine. When you combust it, you produce CO2 and H2O. So we find out something about our carbon and hydrogen in there. So since I have 0.872 grams of CO2, I can find out more about my carbon, take the 0.872 grams, change that to moles of CO2, because remember CO2 is 44.01. So I have 0.0198 moles of CO2, which is also then my moles of C. And then if I want to change that back, I could take the 0.0198 moles of C times 12.01 grams for carbon. And what I really have is out of that 0.872, I have 0.238 grams of carbon. And then the other thing they're asking us to do in part A here is determine the percent of carbon and hydrogen. So my 0.238 grams of carbon out of my original 1.3 times 100% lets me know I have 18.3% carbon. So I'm going to follow a similar process for my hydrogen. And I'm going to take my 0.089 grams of hydrogen, or H2O I should say. I'm going to divide by the 18.02 molar mass, and I find out that that's 0.00493 moles of H2O. And now I see that I get 2 moles of hydrogen for every 1 mole of H2O. So this is 0.00988 moles of hydrogen. And my 0.00988 moles times, I just take 1.01 because I'm talking about just elemental hydrogen here, means I have a total of 0.00998 grams. And again, this is out of the 1.3 grams times 100%. So now my percent is only like 0.77%, a very small amount of hydrogen. So part B of the question asks you to analyze a second reaction where you take this same solvent J, which only has carbon, hydrogen, and chlorine, and now you react it with AgNO3 and AgCl precipitates out. So in this case, I can find out about my chlorine because I have 1.75 grams of AgCl. So I could change this to moles of AgCl. And I find that it weighs a bunch, 107.9 plus 35.45. So it weighs 143.35. So this is 0.0122 moles of AgCl. And then I look and see that that means I get 1 chlorine ion from every AgCl formula unit. So I have 0.0122 moles of chlorine. Go ahead and multiply that by the 35.45 grams per mole, and I get 0.433 grams, and this sample was only 0.535. So when I take this times 100%, I find that the other 80.93% is indeed chlorine. And this matches with what I had up here, that I had 0.77% carbon, and I think it was 18.3%. So this seems reasonable that my other 81% should be the chlorine. So then finally part C wants an empirical formula, or a molecular formula, I guess, if the molar mass was determined to be 131.38. So first I'll need an empirical formula. So 18.3% or 18.3 grams of carbon would translate to 1.52 moles. 0.77 of hydrogen would become 0.76 moles, 0.762 if I keep 3 sig figs, and the 80.93 would become 2.28 moles. So my formula then, C 1.52, H 0.762, and Cl 2.28, dividing by my smallest molar amount, I'm going to have C2, H1, and Cl3. And the mass of that then, 2 times 12.01 plus the 1.01 for the hydrogen plus 3 times the 35.45 for the chlorine is going to give me a mass of 131.38. So this is also the molecular formula. So number 19 gives you this balanced equation. Lets you know you have 30 decimeters cubed or 30 liters of each gas at the same temperature. So we can use molar volumes here. So they want to know which gas is in excess. So if I look at my two gases, NH3, 30 decimeters cubed will produce a 5:4 ratio with the N2, which is what we're interested in. So I can expect to get 37.5 decimeters cubed or liters of N2 from the NH3, whereas the NO, 30 decimeters cubed, is going to give me a 6 to 5, or a 5 to 6, I'm sorry. A 5 to 6 ratio, so this is going to decrease to 25 decimeters cubed of N2. So which gas is in excess? The NH3 is in excess. And then they want to know by how much. Well, by how much, I could take the 37.5 minus the 25, and that means I could produce another 12.5 decimeters cubed of N2. That's not how much of the NH3 is in excess. Now I have to look. I get 4 moles of NH3 from 5 moles of the N2. So now when I take my 12.5 times 4 and divide by 5, the excess would be 10 decimeters cubed of NH3. And then they want to know how much N2 could be produced. Well, we already figured out that we're limited to 25 decimeters cubed of N2. Okay, so number 20 gives you a ton of information, and the only way I can deal with all this information is to start making some graphics for it. So you can think of this as my graphic organizer. So they tell you have 0.188 grams of eggshell. An eggshell has some calcium carbonate in it. It's not all calcium carbonate, but certainly some of it is. So they take the eggshell and they react it with HCl. Now we're assuming that only the calcium carbonate is the only thing in the eggshell that reacts with HCl. And we dump a bunch of HCl in there so that we're sure all the calcium carbonate gets reacted and becomes calcium chloride. So then to find out how much HCl actually reacted with the calcium carbonate, now we have to add NaOH to this excess HCl and see how much NaOH reacts. So this makes sense. We do two different reactions. We put extra HCl in to try and get all the CaCO3 to become CaCl2. And then we take our original solution and we titrate it with NaOH to see how much NaCl forms or how much NaOH we need. So working backwards, they kind of lead you through this. A, they want to know how much HCl was added up here. Right here, question A wants to know is how many moles of HCl were added. So this one's pretty easy. I've got really 0.02720 decimeters cubed at a strength of 0.200 moles per decimeter cubed. So my original moles is 0.00544 moles of HCl. Now that's more than what I needed to react with the CaCO3. So I can't just use this number and calculate my calcium carbonate. Instead, I have to go on to part B, where they tell me that 23.8 centimeters cubed of NaOH, 0.1 molar NaOH was used to consume all of that. So now if I take my 0.0238 decimeters cubed of NaOH times the 0.100 molar NaOH, that will tell me how much NaOH I used, which is going to turn out to be 0.00238. That's my moles of NaOH, and since it reacts 1-to-1, that's also my moles of HCl. It's a 238 there. That was my excess HCl. So now, if we look at A, I added 0.0544 moles of HCl. I knew it was more than I needed. I found out how much extra it was. For part C, I could take my 0.00544 that I added, subtract the 0.00238 that I know I had left over, and I find out that I actually used 0.00306. All of this to find out how many moles of HCl was actually used with the calcium carbonate. So now we can go on to question D. So now part D, they want you to state the equation. So calcium carbonate plus HCl, it looks like it should just be a double replacement reaction with CaCl2 and then H2CO3. But H2CO3 always breaks down into H2O and CO2. So this is an equation you'll become familiar with. But if you didn't know that right now, it's really not going to change anything, because what we're interested in is this 0.00306 moles of HCl that we know we consumed in the reaction. So part E then says, determine the amount in moles of calcium carbonate. Well, if I know I had 0.00306 moles of HCl to completely react with all the calcium carbonate, I see that there's only 1 mole of calcium carbonate for every 2 moles of HCl. So this is really going to become 0.00153 moles of calcium carbonate. So then F wants to know the mass of calcium carbonate and the percentage in the eggshell. So I take my 0.00153 moles, figure out my molar mass for CaCO3, and I came up with a molar mass of 100.09, giving me 0.153 grams. And then you might have to look back and see that was 0.153 out of 0.188. So when you calculate your percentage here, I'm getting a percentage of around 81 or 81.4%. And then G wants to know one assumption you made. A couple assumptions you made is that all the CaCO3 reacts with the HCl. You're also assuming there's nothing else in the eggshell that will react with the HCl. Those are kind of the two big assumptions. All the CaCO3 did react, and only CaCO3 reacts with HCl.